Hello everyone, welcome to the high performance inference large language models. Now this high performance inference for large language model is being presented by our speaker Ravishankar Ravindran. He is PhD and he is presenting on behalf of Emerging Open Technology Foundation as of today, November 1, 2025. Next slide.
Let me.
So, yeah. So
you wanted the speaker first, or
yeah, that's okay. So Ravi Ravindran is a accomplished what you call a engineer, and obviously he's engineer with a PhD, so makes a lot of difference. He has been working currently advising Emerging Open Tech Foundation. Prior to that, he was in FI where he used to manage load balancing and all that. In between, of course, while being in EOTF, he also worked on what you call ORAN working group and Nephew, which is a Google implementation of ORAN. So he has a strong telco background, to put it in simple terms. Prior to that, he was at Huawei, and there were other 5G architect positions. He was in various other companies, but Huawei was a major one where he had a lot of work in the ICN, which is a kind of a high-level implementation naming services. And then he was part of the various, prior to that he was in Nortel, which was a major one in the CTO office. He has more than, over a period of time, he has more than 4,000 citations, and there are something like 90 patents, and still there are many in process, all in the US. So he has been a prolific what you call the he has been prolific in his work and very deep. Please silence, don't. Okay, so
probably you can silence the participants.
yeah, I thought I had silenced everybody. I don't know, new person joined, that was the problem. Okay, let's move on. So please make sure that do not speak in between. Keep your mute when you are in. So he has had a very prolific career, and at this time, last year, last 1.5, 2 years back, he moved his direction towards the what do you call, going more towards AI. Of course, he was in AI, but he did not focus on AI as application and AI systems. He was more on the telco side. Now, when he completed his what do you call, training at Stanford, I believe, and then he jumped into the AI bandwagon. And so, go to the next slide. So I have introduced him sufficiently. He is very accomplished, and you can count him to give whatever best he can present it. So the abstract, I would just put it there. The earlier discussion with I had with him was on the inferencing, and then AI. Then it turned out that he was more focused on what you call models. So he asked me that let us focus mainly on the AI usage, and because there is a model optimization and a system optimization. He's a systems guy, he prefers system optimization. So his view he will present for system optimization, and obviously there are many tools and platforms and services like SGLang, then we have got NIM, then you got what you call the various other service provider platforms. And he'll go through some of the platforms and how they optimize, what is the uh, relation between the various parameters that are used, and mainly because something becomes compute intensive, some of these become more memory intensive, and one has to balance. And some people do batch inputs, some people provide tokens as dialogues. So the different ways of doing with GPU and the platform and the clusters, all those elements that get into is what he's going to bring to us. So at this time, I will hand over to Ravi. Go ahead, Ravi, and welcome, and make your presentation as comprehensive as possible. People will wait. We want you to give them and impart them with the right knowledge. Go ahead. Thank you very much.
Sure. Thank you, Prakash, for that kind introduction. I hope you can all hear me. I see participants are still joining. So yeah, I'll set the stage here with this, just talking a bit more with what Prakash introduced on this slide on abstract. So as I said, as Prakash said, this talk is primarily, in the context of inferencing for large language models, and how do you achieve high performance using different optimization techniques. Inferencing as such, it's something that's front and center for everything that we do, we access today on the internet, right? I mean, it's quite an ubiquitous service, and it's just not when ChatGPT came along that inferencing came to fore. But even before that, you should just talk about any other kind of services where you're doing, like, where you're kind of talking about recommendation systems or any kind of classification and so on. And these kind of inference engine reside today in your devices and different hierarchy of the cloud and so on. But what happened since the ChatGPT era is that there has been inferencing has come online, in a sense that the amount of workload that the inferencing engine has to take to handle the user requests with these large language models and transformers under the hood has kind of exponentially increased, and hence you require hence these inferencing engines have had to introduce several optimization techniques to handle this new increasing workload, right? And the other aspect with large language model and transformer itself is that though initially it was being used for generative tasks related to text generation, but recently it's also being used for many other multimodal kind of applications such as vision and reasoning and planning, and so on. So you will see that. So you're basically even seeing this trend of basically where these models are just not going to be used for, I would say, more like say near real-time kind of application where you're interacting as chatbots and so on, but eventually be used for generating kind of voice and speech using virtual agents. For example, you can consider a good example would be when you do contact center based kind of applications. Those could be actual virtual agents driven on large language models and transformers. And in those scenarios, the service level objectives are going to be more stringent, in the sense like they're going to be more real-time kind of requirements. So you're going to see this inferencing engines going to kind of cater to several kind of different kinds of application scenarios, hence requiring to meet different service level objectives. So in this talk, what we are going to focus is primarily on the system level optimization. Prakash just said that, okay, there are two ways in which people are trying to address this problem. One is kind of trying to optimize on the model level itself, basically taking the transformers and generating and looking at how you could manipulate it or kind of bring out variation so that it is more memory and compute efficient. The other is basically at the system level, how basically drive optimization at the system level itself. And in this context, you see several innovations such as, starting from the very basic things like KV caching or the basic optimizations that are basically being applied at the attention function of the transformer layer, which is we call it as page, flash, radix extension, which we'll be talking about, or things like speculative decoding, or even kind of complete kind of distribution of these functions across the cloud cluster itself. And as also Prakash mentioned, a lot of these implementations, or a lot of these techniques are being kind of applied in kind of some of the well-known open source stacks such as VLLM, SGLang, Hugging Faces, TGI, or NVIDIA's Tensor TLLM, and so on. And these techniques are being used basically at scale by large kind of hyperscalers, I would scale in this space, like OpenAI's or the Anthropics and so forth, or Perplexity for that matter, to kind of to serve requests at scale. So let's go into the next slide. So this is the agenda for my presentation. So I'll begin by basically setting the basic, trying to kind of setting up this idea in terms of inferencing for LLMs itself. It will be more or less what I just covered. But after that, we'll be going into the performance objectives. Exactly what are the performance objectives and inferencing system or inferencing platform uses as a benchmark when you compare among different inferencing platforms, or just considering the metrics from a user perspective and so on. The other thing is the other topic that, sorry, I was just distracted by a question. I'll come to the questions later, as Prakash mentioned. So the transformer, so we'll talk about transformer complexity, right? As I said, a lot of this is to do with how do you address the transformer complexity by different techniques that are applied at the system level or the model level. So we'll talk about this model level system-centric kind of optimization. And then the core of the presentation will be going through the different optimization functions that that is being kind of implemented or is being kind of researched upon to kind of make these systems more kind of operate at high performance levels. And then we'll be touching upon some of the system architecture aspects, considering the implementations we have from VLLM and SGLang, inferencing platform. These are very active projects. I mean, and again, there's with significant participation from the industry, whether from the hardware, software, model service providers, application providers in this space, and so on. So, and then there are you could just search for these and find the GitHub links and join their Slack channels and get the latest and the greatest that's happening in this space as well. So just starting off here, inferencing for LLMs. So basic idea about inferencing is that, okay, you're taking a trained model and are using it for production purposes. And so this is inferencing is, I would say inferencing is one of the key functions where is function where basically you have to kind of optimize considering different stakeholders kind of interests. So you have an inferencing provider who is basically who has built out his basically who has a cloud kind of a platform, or has investment in a cloud platform. There's a lot of GPUs under the hood, compute, there's networking, and there's manpower, there's power consumption, and so on, that's used to kind of drive this these inferencing model. And then there are the users. And so inferencing is basically an optimization problem where you're trying to kind of optimize for the model service providers kind of capex and opex optimize on that front, as well as to kind of meet the user requirements from an SLO perspective. So that's I would say that's what makes inferencing kind of a very complex kind of a problem. But I did touch upon the other points as well in terms of LLMs being the center of focus, as transformers is basically serving as a model architecture for several other tasks, which is, I would say, which should be more used for kind of real-time tasks as well, in addition to what we are used to with kind of near real-time tasks. Yes, SLOs are going to be different, and inferencing can be distributed as well. in the sense that you can apply the inferencing can be applied at different hierarchies of the network layer at the central, regional, or edge or device as well. And inferencing systems. So when you talk about inferencing be distributed, as I said, there's one thing about offering the same service at different hierarchy, network hierarchy. The other thing is that inference system can be for a given implementation of an inferencing system, it can be scaled across different devices also. So the inferencing itself as a function can be it can be distributed at a given location, and which is what I would say is more relevant to this particular talk. And I talked about this optimizing inferencing system, and because, as I said, there are multiple stakeholders, and the objective is to for a model service provider who wants to kind of monetize this, it's about maximizing their revenues and profits while not compromising the SLOs for the end user. So coming to the performance objectives for LLM inferencing system. So the key performance metrics can be related to because most of us have been interacting with services like ChatGPT or Anthropic and so on. So I'll try to relate it to some of the metrics that basically an experience factor from that perspective. So the very first metric of interest is basically a time for first token. So this is from the moment where you have basically expressed a prompt to this system, to a ChatGPT system or any of these other models, and you see the first response, right? So that's when basically that is the time taken from the prompt to the first kind of the token or the word that comes to you can be considered as time for first token. Then you have what is called as inter-token latency. The inter-token latency is primarily about the latency between the tokens themselves. So basically, you see the token streaming to you and coming, or sometimes it comes as batches and so on. But there is a certain though you might see it from a visual perspective, but there is these tokens are generated in a sequential way. So if you were to measure this, the inter-token latency at the inference system level, you will see that, okay, there is a certain kind of a jitter factor, you can say, applied showing up with this inter-token latency aspect itself. So you can think about inter-token latency as the actual measure between token latency, and time per output token is kind of an average of those inter-token latency. And token throughput, there are two aspects of the token throughput. Is basically one is basically the rate at which the users are receiving tokens. So you can say user perspective of the token throughput. The other is basically the aggregate tokens per second generated by the inferencing system itself. So there's a measure that you can apply for the end user and a measure that you can apply for the service provider itself. And I would say accuracy accuracy is another metric. Though this is typically, you don't see, if you were to look at inference system, they don't say accuracy as a metric, but I think it is important, considering that inferencing systems are going to be multimodal in general. So if I have two inferencing systems that can intelligently take my prompt and give it to a model so that it can give a better response to me in terms of accuracy, then that becomes an important metric for me to kind of consider this inference system versus some other inference system. So it is, I would say, another kind of a qualitative or a quantitative metric that can be used to kind of measure the performance of system itself. This is basically considering the fact that these systems are getting as more and more intelligent, and this not simply kind of doing things like managing queues and giving it to kind of a given GPU for basically inferencing or generating tokens itself. Optimization objective, we did talk about that, is to find an operating point so that the SLO is met while maximizing system throughput with the given resource and the minimizing the energy consumption. So this graph that I have here is a very kind of you probably if you have watched any of this inferencing system related talk, this is a very common graph that you would come across in those talks. Is basically the Pareto frontier. The Pareto frontier is primarily showing a trade-off between the two objectives. So idea is that I have one objective where I want to kind of maximize the tokens per second for a single GPU. The other objective is that I also kind of is from a user perspective, where I want to maximize their tokens per second. So increasing the tokens per second for a single user would be kind of reducing the inter-token latency that we talked about, right? And for a different system of configuration, you basically come up with this Pareto frontier where you cannot do better than this, in the sense that for a given user, basically for desired tokens per second that you want to kind of maintain for a single user, then there is a certain throughput. There's only a certain throughput that you can achieve for that particular system. And this has to do primarily with the multiple factors. One is the limitations of the GPU resources itself, and second is primarily to do with the operation of how the functions have to be computed within the transformer itself. So so any of these points, if you look under this Pareto frontier, are basically are points that you would get because of a choice of different, I would say, engineering configurations that you make within that within the inferencing systems. For example, for different kind of batching that you might want to choose, or for scheduling or hyperparameters, leads to different operating points. The basic, I would say, from an inferencing service provider is that you're going to kind of have certain I would say a certain benchmark you would want to reach in terms of you wouldn't be kind of over engineering system to give performance that is beyond the physical ability of the user of the end user itself. For example, a user generally has a capacity to kind of read, say, 4 or 5 words a second. So that would basically translate to something like 20 to 50 tokens per second or so on. So that's basically saying that as long as I'm able to generate an inter-token latency of around say 40 or 50 milliseconds, then that should be good enough. And that's generally the kind of when you plan the systems, when you capacity plan the systems, and when you say that, okay, for a given set of users, how much GPUs I want, how many servers I want, and so on. These are the basic criteria that you would be considering to plan your system, so that you don't over-engineer it, or you don't spend unnecessary amount of kind of monetary resources towards building your cloud infrastructure. So we'll now look into a little bit on the transformer complexity itself. When you're talking about the key, when you talk about the transformer, I'm not going to go into the fundamentals of how a basic transformer operates here. I'm assuming that folks have a understanding of that. But here, basically, what I'm trying to highlight is the most kind of the compute and the memory intensive operation of a transformer, and the parameters that is used to kind of quantify that using a big O notation, right? So basically, the key parameters, if you were to kind of consider from that perspective, would be the batch size. So batch size can be considered as the number of requests you're going to handle at a given point of time. And the sequence length is basically the number of tokens you're going to kind of process to generate the next token. And then you have something like the hidden dimension. So if you know the process at how a transformer actually works, so basically whatever words that you are, the words that that come into the system is initially kind of tokenized. And when you say tokens, those are basically mapped to certain integer values based on the specific models vocabulary itself. And those kind of tokens are mapped into certain embedding vectors, and these embedding vectors have a certain dimension, and that's what is called as a hidden dimension D here, and the number of layers within the transformer itself. So basically, if you just take the decoder portion of this transformer, this entire thing would be kind of the sync considered as one layer. Okay, and the most I would say the complexity, the compute and the memory complexity of the transformer itself is dominated by the attention function, which is basically which is here, which is called the multi-head attention function itself. And generally, this has a complexity of basically increasing or growing exponentially at the rate of quadratically at the rate of n square. And similarly, you could see that complexity coming in both at the compute in the compute aspect as well as the a memory as basically the amount of resources required for the memory operation as well, right? So so as I mentioned here, so the first term here is basically capturing for what the kind of the complexities that is within this. I mean, say within this bigger notation, there are two terms here. So the first one is basically a contribution from the attention operation itself, and the second from the QKV projection kind of function. So this is basically from the QKV. If you know how the things that happen within the attention layer, particularly in the very first step, you are taking these embedding vectors and then you're basically multiplying them with some WQ, W key and WV kind of matrices, and these matrices have a certain dimension, and this is what is the complexity of this part comes from that multiplication. And so the feed-forward complexity is not being considered here generally because we are talking about the big kind of the complexity, the dominant part of the whole model architecture here. So if you look at it, so there are two parts of this. Again, when you talk about the token generation process itself, there are two parts of the token generation process. So one is called as a prefill kind of the phase, and then the second is called the decode phase. And for the again, just to put it in a more kind of a practical context here, prefill is basically when you comes into play when you first submit your prompt, and the inferencing system is going to take that and basically tokenize it, and when you basically process it, you don't have the initial set of KV kind of you don't have the K and V matrix that is computed, and it has to be done for the very first time, right? And that phase generally is called as prefill phase. So you take the prompt, you tokenize it, you basically you with the embedding vectors, you give it to the GPU. GPU comes up with the very first token. The entire phase is called as a prefill phase. And then once after the prefill phase, what happens is that you enter what is called as a decode phase. So in the decode phase is basically benefits for the fact that you have done this computation to calculate this the key and value matrices. And then the fact that, at any basic fundamental implementation of inferencing systems would have that you take this key value matrix and basically reuse it in the decode phase. So then things get incremental because there you are doing kind of much less compute operation in just generating the next token and so on, using this history of KV values that you have. So so then I'll kind of have your focus here within this graph, so I can go into this now, having set that stage. So prefill is a compute bound stage, and decode is a memory bound stage. So in this domain of basically compute, what makes the GPU operation a compute bound, a memory bound, is actually quantified by a metric called as arithmetic intensity of a GPU. Okay, and this is very kind of, I can say, it's a function of the hardware features itself. So basically, the basic benchmark is that if I take the total flops offered by the GPU and divide it by the memory bandwidth, that basically gives me the kind of the benchmark of that arithmetic intensity for the particular GPU. And yeah, so if you're so here, okay, now I'll have you focus in this particular graph here. So basically, what this graph shows is basically for a given kind of an operation that you're basically conducting on that particular GPU, you can actually have that operation lying either as a compute bound operation or a memory bound operation. So basically, if you have an operation that is achieving an arithmetic intensity of probably greater than whatever is you compute as part of that GPU, then you basically are within this compute bound regime. Else you are falling in this memory bound regime. The basic idea here, just think about this idea, is that, okay, if I'm multiplying two matrices, like I have basically A cross B matrix and I have a B cross C matrix, right? And basically the amount of, if you take the total compute operation on this matrix, is basically a dimension of basically A times B times C, right? And the amount of data that I have to transfer from the high bandwidth HBM into the core or the GPU compute units is basically your A times B plus B times C, right? So for a given operation, you can actually compute what the arithmetic intensity for that given operation is, and basically in that case, if it's ABC divided by AB times BC, and if that operation, that whatever you calculate is basically less than this the maximum arithmetic intensity required to keep the GPU busy at the 100% utilization, then you're basically falling within this memory bound regime. Else you're falling in this compute bound regime. And this why this is relevant to this transformer is that, as I said, this prefill phase is pretty compute intensive. So basically, for the amount of data, the problem is that you basically have n tokens, you have the embedding vectors n times dimension. You basically move it into the GPU, and basically you do this kind of the attention operation. You are basically taking the query times k transport divided by v. That's the basic operation you do. You can be sure that the GPU is operating at this compute bound regime. For the data that you transferred, the amount of operation for multiplying, transpose, and doing all the kind of my matrix multiplication is pretty compute intensive. But there's always this thing that, okay, so prefill is compute, prefill is kind of operating at the maximum GPU, it gives you a maximum GPU utilization. But decode, what happens with decode is that, as I said, like once you have the key value kind of matrices computed, you're reusing it in the decode phase. Again, I hope people understand that why we have to use that key value matrix, because transformer itself, the whole operation operates in an auto-regressive manner. So you're based on the history of all the previous context window you're seeing, you're basically generating a next token. So I'm moving this entire key value matrix into the system, but then I'm only generating one token out of it. And that makes it, the amount of the compute that is used there is very less compared to the amount of data I'm moving. So even if I were to kind of batch this kind of movement between the HBM and the GPU cores in terms of compute and communication and so on, you would see that GPU being not fully utilized, because the transfer is going to take much longer than the amount of time you're spending in compute. So that's where, so a lot of the optimization that you see that I'm going to discuss about is about how do you kind of improve this regime of operation. And the multiple ways you can do it, either is that, okay, you increase the memory bandwidth. So this would fundamentally mean that, okay, I'm coming with new iterations of the GPU. So example, if you have the Grace Hopper kind of, you have the Grace Hopper kind of the family, then you have the Vera Rubin coming next. You have, sorry, the Grace Blackwell, I think GB it was called, or Grace Hopper also, I guess, and then Vera Rubin. So there's multiple kind of generations of the GPU coming in that NVIDIA is putting out, probably AMD, and many kind of startups are also coming up with many kind of inferencing kind of hardware just dedicated to kind of to cater to the specific requirements that you need this very high bandwidth memory and so on. The other thing is that for a given hardware, what else can you do? You can reduce the amount of data that's being transferred. As I said, like you reduce the communication cost, or you basically do more kernel intelligent operations. So you basically do things like fuse kernel. We are some of the techniques that we'll be talking today. So I hope this gives you a very kind of a big picture and gives you a very this understanding of what a prefill is, what a decode is. That prefill is compute bound, decode is memory bound, and so on, and where these optimizations are kind of trying to address the problem in the big picture. So okay, yeah. So then we mentioned that, okay, there are two kind of I would say kind of levels of optimizations that are being kind of I would say investigated by the research and the industry and so forth. So one is basically taking the transformer layer and seeing exactly how do I kind of we did talk about the fact that attention is the most basically the most costly aspect of the whole transformer model architecture and so on, or the algorithm itself. And to see that how do I kind of make this attention operation as cheap as possible, as was less expensive as possible. So you have many kind of proposals in that space. So with things like mixture of experts, group query attention, multi-head, latent attention, cross-layer and local attention, and so on, or quantization for that matter. This picture would give you an idea of the different kind of a visual kind of an idea of how the different variants of attention itself is leading to kind of less key value demand from the caching perspective itself. So basically, when transformer initially was proposed, it applied something called as multi-head attention. So basically for every, so you take the entire the query kind of the matrix, and you basically slice it into multiple heads, and the query head had a key head and a value head. And then people moved into what is called as a group query attention, where you, for multiple query heads, you're basically you kind of had a specific, you only used a factor of attention of basically the key and value heads. And then they moved into a more kind of extreme scenarios where you're using just one key and value head. So the idea is that you cannot do much with the query, because this is the kind of the workload that's coming into the system. These queries are going to be what it is at a given point of time. But this is a system parameter that you can probably change, because you've changed the internal architecture of the transformer itself. And then you have something called as multi-head latent attention. This is something that's kind of was introduced with DeepSeek v3. So the idea is that though it shows multiple KV heads for each query head, in practice, what is there? It's very much similar to this. Actually, it's a much kind of the projection vectors or projection matrix is much lower dimension than the standard multi-query attention head itself. So it's much kind of, I would say, more memory efficient from that perspective. So there is multiple of these proposals just focused on kind of making the attention kind of the function more compute and memory efficient. The other set of optimization that we'll be focusing on here is related to the system optimizations itself, in the sense like what we can do at the system level given for a given model. And generally, you would expect that a lot of these system-centric optimizations are model agnostic. So basically, given an inferencing system and basically saying that, hey, this inferencing system is basically it works on basically models that are based on transformer kind of an architecture, you should be able to take it and serve it at scale. So that's the general idea here. But sometimes you have to kind of, it's not as simple as that. Sometimes you have to take these systems and probably tweak it, or basically refine it to kind of handle new variations of transformer model that is coming into, that's basically being introduced by different community members and so on. And if you look at this optimizations itself, which we'll be talking about soon, can be categorized following into different layers of the stack itself. So some of this optimization, you can see it happening at the network or the nodal at the network level itself. So basically, as I said, inferencing, for example, what we have is basically the prefill and decode disaggregated kind of serving or inferencing itself fundamentally kind of creates multiple clusters of this inferencing of the inferencing system to kind of handle the user workloads. And there's a lot of innovations happening from the KV routing perspective, application protocols to interconnect all these distributed systems. And then you can think about other things like what is happening at the node level itself. So every node level has an inferencing system. You have a scheduler, you have prefix caching, paging, and parallelism that comes into play, say something at the node level. And then you have the transformer level kind of implementations that we talked about, like some of these, what we mentioned here. But in addition to that, you can talk about the model level. There are other techniques that can be used where you're not fundamentally changing you're not focused on changing the model architecture itself, but things like speculative decoding falls into that category. Kernels, I would say this is very critical part of kind of making the systems operate at a very high performance mode, because at the end of the day, if you look at you run any of these scripts, or even if you just have one, if you simply even have your PyTorch script and basically with a GPU under the hood, then basically the PyTorch is going to kind of invoke several of those the CUDA kernels to kind of have this arithmetic operation being executed, and so a lot of it is kind of can be you can get a lot of gains by having more kind of efficient kernels being implemented, so that a lot of the operations that were done in probably multiple stages can be done in a single shot, for example, using fused kernels and so on. And of course, then there's optimization that can also done at the fundamental hardware level, where you can have a virtualization layer and basically you can have the system operate and cater to multiple tenancy and things like that as well. So Kubernetes, for example, is another layer, and there's one project LLMD that I'll be talking about where this is being done at that virtualization level. So I hope this gives you a big picture of how the whole optimization space is kind of broken down when you talk about inferencing optimizations for LLMs. So we'll go to the first topic of basic KV caching. So what is fundamentally KV caching? I think I explained this a bit. So basically we have two phases of operations here. One is a prefill phase, and then you have the generate phase or the decode phase. The basic idea is quite simple here. So idea is that when you do your prefill is basically, when I said, like, you take this particular prompt and you put it to a transformer, and you generate your initial KV cache, and then you have your logits. So logits here are primarily those probability distribution you get for every token that you input into a system. The system is going to give you the logits on basically probability distribution over the vocabulary that this particular model is trained on. So this is nothing but a probability distribution, and based on the probability distribution, you can sample the next token. And generally, there are multiple ways you can do sample as well. Which you generally that you come across in this particular literature. So idea so this is, we don't want to focus on the actual sampling part here, but the idea is that this KV cache that is computed in the prefill phase is then reused during the generate phase or the decode phase itself. So and idea is that you've taken the next token that has come out from here, and then all you have to do is to calculate the key and the value kind of vectors, add it to this key value pair, and then run it run it through the attention mechanism and the layers of the transformer to give you the next token and so on. So what does this kind of give you? So if I were to not have something like KV cache, then every kind of iteration is going to be like a prefill, right? I mean, you're going to get, everything is going to be compute bound, but then when everything is compute bound, you're also going to suffer on the intertoken latency. So the idea is that this is why you also have these two metrics to calculate your prefill, as well as to basically quantify the performance of the prefill phase and the decode phase. So the first token is always going to be the most expensive part, where you have time for first token. But then because you're using this kind of the KV cache values into the future processing of your step in the decode process, your intertoken latencies are going to be much less. So again, the other important thing is that you can say the flip side of doing KV caching is that it also demands a significant amount of memory. So if you're basically having you're doing 10 batches of requests at the same time for every batch that you're servicing, and if all of them are in the decode phase, then you have to consider the KV cache memory requirement for all those 10 requests, and this leads to a lot of, say, tens of gigabytes of memory that will get used or needs to be reserved, or to be kind of reserved for the KV cache tensors that you are calculating in the prefill phase, and this kind of increments as through the life of the generative task itself. And has to be stored in the HPM. So so you gain on the latency. The latency of the intertoken latency is going to be much lower, but this comes with the fact there's a memory trade-off that your amount of memory that's required is also going to increase as you go through the generative task. So yeah, so I think we covered most of the points here. So the next optimization that I'll be talking about is the continuous batching and the chunk prefill. So as I talked about, like the decode, we talked about this decode itself. The decode is going to operate at a memory bound level, right? We talked about the fact that, okay, the arithmetic intensity is going to be lower than what is the desire to keep the GPU fully utilized. So one way, so this goes to the, we went through this the complexity here. So in the decode phase, your n is going to be 1. So it's now your complexity. You've removed the most expensive part of this complexity here. So this is what reduces your compute complexity, right? But now what you have to do is to find ways in which you can increase the compute work that can be done by the GPU. Because if you're just doing one request at a time, it's going to give you the best performance for that request, but in terms of the actual throughput of the inferencing system, it's not going to be great. So that's where you have to you start batching requests at a given point of time. And batching, as you know, is going to be a little bit of a it's kind of a random process, because at a given point of time you don't know how many requests. But if you're going to have multiple requests, probably you can accumulate some of the requests and then do your you get start on with a generative task, right? So so this is basically going with different kind of let's say, can say, the drawbacks that is introduced by the basic vanilla based batching versus something that you would do incrementally to to address some drawbacks that's coming from the basic ways you can do it. So static batching would be that, okay, you just take a bunch of requests that is the waiting queue of the system, and then you start generating text, or basically put it to the transformer and the GPU itself. So for example, this is basically just showing, this is showing for the continuous batching, but if I just do a static batching, it basically would mean that, okay, I take this 4 requests and sequences or so on, or S1, S2, S3, S4 could be different. I mean, you just think it in terms of the different requests that is coming into the system that you're serving, and you basically batch it and you start generating tokens. So as you see here, that initially, I think the color coding is such that yellow is being shown, okay, what is the kind of the time being spent during the, say, for the pre-fill phase, and then you're basically going into a decode phase and so on. So static batching, the drawback with the static batching itself is that if you have a single batch, one way you could do batching is that you take this request and wait, and I wait till all the generative tasks in that particular batch is finished. So in this particular case, if I were to take the straggler here, would be something like S2 that is having the longest generation of sequences, and I wait till I start introducing some other new requests into the next iteration and so on. So that's what the continuous batching kind of addresses. So this seems to me that then you're not using the GPU resources well. So at every iteration, the inferencing system is going to check whether, okay, which of the requests have completed has achieved that end of sequence has achieved the end of sequence kind of token, so that, okay, this task has finished, and now I could respond back and basically take it out from my processing queue, and at this particular point I could introduce a new request into the batch itself. So this basically ensures that at every iteration you are occupying, you are basically having some tasks, you basically entire batch, I can say the batch, your batch is always is fully populated with active requests being processed in every iteration. So so the other thing is that user requests are random and have different ISL and OSL distribution. So this is again going back to the fact that, okay, this is again going to the actual drawback that comes from the static batching itself. But the new term that I'm introducing is basically, what is the ISL and OSL mean here? So ISL primarily means the input sequence length and output sequence length, and these are kind of, I can say, they are random variables, because to begin with, for a given inferencing system, you can't predict what the prompt lengths are going to be. For example, a simple prompt length could be people just sending kind of few tens of tokens, versus if you were to look at some kind of RAG kind of applications where people probably must be sending text equivalent to what is coming from a PDF document and so on. So those could be have very high levels of very high lengths of ISLs. And OSL itself is basically about, for a given prompt, what is the distribution of output tokens that I'm going to generate. So these are both kind of random quantities that cannot be are indeterminate, or you could probably kind of bound it with if you know the use case scenarios in which the inferencing system is operating. So yeah, so this is what the continuous batching is about, to keep your every iteration to make ensure that in every slot of the batch you have at least one user getting service. But there's again some drawback that comes with continuous batching itself. So the basic drawback is that again, in this inferencing system itself, sorry, I'm introducing many ideas here. So there is a scheduler that comes into play, okay? And the scheduler is basically it's like any other thing, because you have user requests, you have service that's being basically done by GPU resources, and the scheduler has to choose from this incoming requests or the waiting queues who is going to be serviced at a given time. And if the scheduler is not making a difference, is not going to differentiate between the prefill kind of a compute that's required for a given request versus the decode kind of compute that's required for a given request, then you run into this particular problem where, for example, request R1 is already in the decode phase, and that's what is represented by this blue rectangles. But then you have new requests coming in, which is basically a new request, so it has to now go to the prefill phase. And since prefill itself is going to it's based on, say, the ISL of the prefill, you could run into issues where you're taking the entire KV cache. So there's probably not much room left for continuing the request R1 itself, right? So then you basically have to kind of, in some sense, interrupt, or you have to interrupt the processing for R1 and then continue in the next phase of iteration itself. The other you see this again coming with R2, and then if you go into R3 as well, you have similar kind of consequence happening, and which is very highly inefficient. So the solution that folks have come up with is called a chunk prefill. So what chunking is that? So when these requests are coming in, you kind of the scheduler gets a little bit more intelligent, and it breaks down the prefill phase itself into multiple chunks. So basically, if you look at it, this prefill itself is broken down into much smaller tasks here. So now when you're doing your batching operation in every iteration, the scheduler can now accommodate the request that is already in the decode phase, or the new request that is in the prefill phase itself, without kind of having an effect on the you can say the inter-token latency, or the time to first token for this for the R2 itself. So again, certain benchmarking has been done, and then you can see the chunk prefill can achieve 2x performance in terms of latency in the large batch size regime. Again, there is a flip side that that there might be a certain hit on the time for first token, because now you have that basically the prefill itself is going through multiple phases of basically getting chunked and then getting processed and so on. And so the TFTT might suffer a bit, but generally overall, if you take the average, the tokens per second or throughput for the user would still be within desirable limits. So I hope you get an idea of what the basic drawback of static is. Why do we need continuous batching, and what the problem it brings on board, and then how it's addressed using chunk prefill. Okay, so the other optimization that is very popular, and this is that was introduced in this particular paper And this, I think this was primarily, I'm not sure this was a genesis of VLLM. The two projects, VLLM Energy Lang, were two projects that came out, that's from UC Berkeley and out of the Sky Computing Lab. So one of the kind of you'd say the differentiators with VLLM was when this particular function got implemented called as page attention, and they were addressing a very important problem of how the kind of the memory that is basically dedicated for the KV caches itself was being used inefficiently when we go with an approach of statically allocating memory for memory for the different requests that is coming in. So, so before page attention, there were certain implementations of these inferencing systems, and the way they were kind of reserving KV caches was considering the fact that you can say that the memory was being reserved considering some worst case scenarios. So basically, you don't know what the OSL is going to be, but you assume that, okay, it's going to be probably around 2K tokens. And now if I have, and if you were to basically calculate the amount of memory that's required even for a single token, it's basically twice of the, it's basically two here is basically multiplying the total memory that's required for key and value. But essentially for a single token, and for a given, say the key tensor, it would be the number of layers times hidden dimensions times 2, which is basically considering if you're operating with a numerical precision of FP16. So, and then you basically multiply it with 2 to basically account for both memory that's required for key as well as value. So the idea is that if you might probably, this might come when I read this, when I started doing this, looking at it, I mean, each token could take up to like 800 KB or 1 MB more. And if you look at it for every model, these are all fundamentally different. If you take a trillion parameter model, it might have like probably, I don't know, close to 100 layers. Interdimensions could be like around 10,000 and so on. So this is a variable quantity for a given model. But itself, but a single token itself, I'm talking about single request, single token. So, and if we were to consider that a basic model is going to generate 10,000 tokens, then basically you have to multiply this with 10,000 to basically say that a single token, single request could easily take up to like say 10 gigabytes or something like that in current in current scenarios, right? The way systems are generating tokens and things like that with reasoning and planning and all that. So these systems were kind of the earlier systems were kind of assuming these worst case scenarios and primarily kind of reserving for when a request comes in, it would just statically reserve something like 1.6 gigabytes for that given request. Okay. Now, what happens with page attention? So this idea is primarily coming from the fact of how pages are basically virtual paging happens for process management within operating system itself. That's basic. I would say they always refer to that as the genesis of this idea, is to basically take the entire memory map of the GPU, or basically the KV cache, the memory that's used for the KV caches, break it down into certain blocks, and then you do a paging on the CPU side of things. So this is what the basic idea of page attention means. So memory manager, so there's a memory manager that operates in the CPU side of the system. It maps the tokens to the KV memory blocks of the GPU. And so from the CPU perspective, you see a logically contiguous sequence of pages, but in physically those pages itself is mapping to discontinuous memory, physical memory blocks. So then you have basically once you have some kind of paging that you have in at the CPU end to refer to, you could also use it for some other use cases. For example, decoding process itself could have multiple ways you could go through the decoding process using something like parallel sampling, beam search, and prefix sharing, and so on. So the basic use case here is that the pages that you have, the KV allocations that you have made for the different kind of generative requests can be reused for some other requests as well. So if you do things like parallel sampling, where for a given request you are generating multiple responses, then you have some common prefixes that you can share for that given generative task. Or when you do beam search and so on, you have a similar scenario. So yeah, so this is basically, it has the basically a good kind of you can say there are multiple use cases of reusing this particular idea, not just from the fact that you can increase your throughput or increase the number of kind of requests that you could serve for at a given point of time, but you could also use it for these other use cases. So I just probably I have this figure, probably I didn't go through this figure. So all this particular figure says that, okay, if I have an A140 GB kind of a GPU, this is the total memory of that GPU itself. There is some fixed cost, a fixed memory that I have to use to kind of store the model weights. So this is basically something that's always fixed. So once you load the model into the GPU, it's going to take some fixed memory resource, and then based on then the remaining resources what I could have to play on a dynamic basis for my token generation, and that's where you're basically going to use the resource for the KV caches itself. And this basic diagram says that with kind of static based approaches, you soon run into, say, the memory getting saturated very fast because of this static allocation approach. But once you, with their system of implementation, where you're using this kind of breaking down the physical memory into blocks and then paging it and so on, you could squeeze in more number of requests for that given kind of limit, for the given fixed memory resource that you have at your disposal. So you have better usage in terms of the memory itself, and also kind of increase the total throughput of the system itself. So which is what you want, which is highly desirable, right? And so this particular picture shows the same thing for different implementation, how the inefficiency of how the memory is used because of the static reservation policies. And with something like VLLM, your KV cache usage can be as good as, say 96.3% and so on. The other idea that you could use with something like paged attention is also towards what is called prefix caching. So prefix caching is so when I talk about parallel sampling, beam search, and so on, these are basically using the KV blocks as long as within a single kind of a generative task. Now, prefix caching basically goes a step beyond and basically says that how I could use that across multiple generative tasks. So in the sense that you have prompts that are coming in that share a common prefix and so on. So in this case, you could create kind of a new data structures like a simple hash table, for example, and within the hash table you can store the hashes of those prompts that are being serviced at a given point of time in terms of using the block hashes. And then when new requests are coming in, you can do the hash on those tokens, and you can compare it to the hash tables to see if what is basically the current set of requests that are being processed. And then you can avoid, the idea is that to avoid computing the KV cache values. So you simply kind of refer to those memory blocks in the high band, in the HBM, and then put it through the prefill or through the decode phase. And the idea is that so once you are kind of saving this KV caches beyond after the life of a given generative task, then it means that it's good when you're operating at low request per second regime, but then once you have very high workloads, then you also would run into scenarios where those caches have to be evicted. And there you might have to use some techniques for aging, like least recently used techniques to kind of remove those caches. and when you remove the caches, then you don't have any more block hashes for those caches. Then the new requests have to be done beginning from the prefill phase where you are computing this KV caches freshly and so on. So this is the basic idea of how page attention works. And this is basically giving you more the system level view of things. So at the system level, you have things like a scheduler. This is mostly basically say that what is the internals of a VLLM that are basically an inferencing system that implements a page attention. So you have a scheduler. We talked about scheduler a bit. So scheduler is fundamentally important because you have user prompts. It's the one that decides which request gets serviced in a given iteration at a given point of time or in a given iteration process. And then you have the KV cache manager that manages the block tables. And this is basically doing this logical partitioning of the block tables of the GPU resources itself and keeping a basic track of the free memory blocks and allocating them to the request as and when the request comes into the system. And then you also have a GPU block allocator. And this is primarily important as I talked about eviction. So when you're evicting the KV caches, sometimes you don't have to actually totally kind of delete it, in the sense like you don't have to eliminate it completely from the system. Instead, you could do a swapping kind of an approach, take it to, say, the memories, the CPU's DRAM, save it there, and then and bring it back when you have to kind of reload it back into the GPU when you have to use it. So a similar map can also be managed on the CPU end for this kind of swapping purposes. So one engineering parameter that you need to consider, the configuration parameter, is what is the block size. So when you talk about block sizes itself, as I said, this is the physical KV blocks that basically is a mapping on the GPU's memory itself, and every block is actually designed to or configured to handle 16, 32, or 64 tokens. So this is basically there is a certain trade-off that you will incur based on the choice of this block size itself. So if you have and the reason why this trade-off occurs is primarily because when you're doing these things like block hashes, when you're actually creating these block hashes for later use, if I have longer block hashes, would mean that I'm going to kind of do kind of my prefix sharing is going to be based on much longer kind of longer size of tokens, right? So, but then what happens is that a longer block size would also mean that you're not going to do block hashes until the entire block is also full, right? Because you don't create the block hashes on incomplete, so these kind of blocks. So there is a trade-off in that sense. The other aspect is basically the number of references required by the GPU itself. Now, basically, if you look at a single request, it's actually interspersed within the memory of the GPU itself. For example, this particular request here is basically spread out in block 1, block 3, and block 7. So every time the GPU has to kind of use it for decode generation, so it is going to read different parts of the memory. So memory references is going to be costlier. So if your smaller block size would mean that you would have more references to do, and you might also have there might be other consequences when you were looking at it from a prefix sharing perspective. So this particular picture shows how this memory is used across different requests, and this particular picture shows exactly how this is used when you have request that is having a same set of prefixes. So in this particular case, you can see that you have a prefix that is same, so you can refer to the same block here. But once it diverges, then you're basically doing something like copy on write and creating a different set of block for that particular request. But fundamentally, two requests can kind of multiplex on the same or basically share the same KV block, because as long as they are positionally same. So the other important thing with when you're doing this prefix sharing is that we call it prefix sharing for a reason, because prompts are always have a positional consequence. So if this kind of set of tokens were to come in some other request, not in the first as a first four kind of words, but somewhere in between, then this doesn't work. It doesn't work because when you're generating the next token, it has to be in the context of what you've seen, basically in a historical context, or what you've seen earlier in an autoregressive way. So that's the reason you're always trying to kind of compare it from a prefix perspective to kind of reuse these blocks that for which you already completed the KV caches. So I did cover all the key points that I had to mention on this slide. Okay, so the other kind of improvement that has been proposed going from page attention is radix attention. So this is a proposal that came out with this ST-Lang paper. The idea is that when VLLMs and when the VLM implementation and the page attention kind of was proposed, it's primarily the basic set of use cases were kind of, I would say, more or less kind of focused on a single user kind of interaction. So you're trying to optimize on basically given a set of requests that comes in, how do I best use my available memory resources? But then the set of use cases kind of varied with time. We had more use cases that kind of map to things like few shot learning, something like self-consistency, and this is, I think, very similar to things like parallel sampling, or multi-turn chat, or tree of thought kind of reasoning, and so on. And things even today, if you were to think about system, when you're talking about kind of instruct models and so on, the systems are actually generating a lot of tokens before they give you actual response. So there is a lot of in the sense that there is, or if we talk about agentic kind of applications where there's a lot of, in the sense like those systems can be considered, there's a lot of back and forth that goes between the agent and the LLM itself, but kind of carrying over all the historical data that you have generated so far and giving it to the system, right? So in those scenarios, what happens is that there's a lot of chat history that goes on with every generative task. And this particular proposal was trying to optimize for these kind of emerging scenarios. Yeah, so as I said, page attention primarily optimized for single prompt requests, but Radix was trying to handle these more kind of advanced set of chat situations by preserving caches across user caches. I would say an idea similar. I think it's similar to prefix caching, but it was more kind of I would say they took a more kind of advanced approach by what they call as by handling this using a radix tree. So as during the inferencing process itself, the system is maintaining this a tree of chats or we can say generative tasks it has seen earlier. And so you can say that, so radix tree manages the mapping between sequences of tokens and KV cache tensors. So every node here is actually mapping to a KV cache tensor in the GPU. Again, this process comes with the drawback that's going to be highly memory intensive, because you're going to kind of manage going to manage kind of this memory of the system beyond even after the generative tasks have completed, to basically just to cater to the fact that, okay, you still have the same endpoint probably going to send back my previous history of tokens that I've already seen, right? So so cache tokens and active requests kind of share the same memory pool. So cache tokens are, we can say, things like for which the generated tasks are finished. Active requests are ones that is currently active, but yeah, they have to share the same memory pool. This we talked about, similar to the page attention mechanism. The tree itself is stored in the CPU, in a CPU, and table map the nodes to GPU. So the key idea here is the kind of scheduling mechanism they use, right? The scheduling mechanism is used to prefer longer prefix match requests prioritized to maximize the cache hit ratio. So given a given point of time, you have this very extensive tree, and a new request comes in. And if the new request, if we have two requests that comes in, and basically one request is matching this particular branch, so you basically are hitting a lot of tokens in this particular branch compared to this branch where you're hitting few tokens, then somehow the scheduling system is going to kind of prioritize your request because you're achieving it to achieve a high cache hit ratio. This again might be good from the perspective of the amount of resources you have been now dedicated to even in the GPU to save those KV caches, and you're trying to reuse it as much as possible. But it might also lead to some unfairness scenarios where users might be a little bit starved if you're going to just maximize your cache hit ratio and so on. So again, scheduling, I think, is a very interesting problem in this space, and based on the different kind of use cases, it's an open area of research as well. So. Again, so another technique that is used, this I just brought because, as I said, there are multiple layers of the inferencing stack that's being optimized here, right? So, and this flash attention falls into that category of basically using very efficient kernels. So, and these categories of kernels are basically called as fused kernels because the basic idea here is that if I were to take a naive kind of kernel implementation and how an attention operation would be would be realized using that naive implementation is that I would go through a sequential process of doing the attention kind of a computation. So I would do a matrix multiplication, I will do some kind of causal max, I'll do a soft max, I'll do a drawback, and then I do a matmul. So the entire operation is going to be kind of sequential, and the time required is going to be significantly higher. Whereas compared to something like a fused kernel that this flash attention paper proposed. And what you do in this fused kernel is that you do all this operation within a single shard. But it's not that, so you can't, there's no free lunch, right? I mean, you can't take this entire matrix and do a fused kernel approach. So the way they do it is basically a kind of a more divide and conquer approach where you take the entire matrix, break it down into tiles, and then you apply fused kernel on top of it. So this is basically showing the basic idea here. So if you take a naive implementation or the basic implementation, let me not call it naive because it's still probably at the kernel level, these are still operating at a very high kind of operational speed. So you generally what you're doing is that you're taking this QK matrix, you're computing the attention weights, and then you're basically writing back, and then you're loading it back. And basically doing some softmax operations, and then you basically generate your final embedding vectors with the attention computed on those embedding vectors, right, for the specific token. So this is basically this is resulting in a lot of matrix basically you can say a memory IO operations that is required to kind of make this kind of operation happen. Where flash attention, what it does is basically to, as I said, the basic idea is that you break down the entire matrix as tiles, and then you operate on this tile. So here KJ VJ would mean that, okay, I'm moving a tile of the key vector and a value vector, and then I take the Q vector, I calculate some intermediate values. So when I'm writing back, I'm not writing back big matrices. I'm writing back some temporary values, more or less like scalar values, and then I'm just reading them back to do the next set of operation and so on. So that is the basic idea of what flash attention does. As I said, it primarily trades off memory read-write with compute, so highly memory efficient but compute intensive. Optimization reorders the query key value matrix into tiles that fits into the GPU SRAM. So this is a very important thing. is that you're doing an operation so that it can all fit into the GPU as RAM, right? So if you look at the hierarchy of the GPU memory system itself, you have the high bandwidth memory, then you have the SRAM, which is the layer 2 cache, and then you have the layer 1 cache, which is primary registers. This, and the way and the basic I would say is that there is an order of bandwidth difference going from the HBM to the GPU cores versus going from the SRAM to the GPU cores was L1 to the GPU core. So it gets faster by an order of magnitude. So idea is that so if you can get the data into the SRAM and then just use all the compute resources to calculate it, and then write this small memory tiles back into the HBM, that would give you the maximum kind of I would say, if you talk in terms of compute arithmetic intensity, that will be the maximum bang for the buck kind of thing. So so it computes, applies softmax on the fly without storing the whole the query key value, implemented as part of the attention kernel, improves attention latencies by you can improve it by 6x. You can just do kind of relative compute here, and lower training time. So this mechanism was introduced when distributed training was at its peak, when, or you can say that where if you folks are aware of how of training of models happen, particularly if you're talking as the number of the time required for training a model is directly proportional to the size of the model and the amount of data you want to kind of train on. So, and if you are aware of how, for example, there was, if you read the SICOM paper from Meta last year, I guess, you had, they talk about applying probably around 24,000 GPUs or so on for the Llama, the biggest Llama models and so on. So, so idea was that, hey, for the training, this was a big kind of a value. Basically, it brought in a lot of efficiency by bringing down the training time by certain X factor and so on. And of course, it's not just training. I couldn't get a kind of this kind of performance gain from inference, but for inferencing, this is a very default kind of a mechanism that is used even for inferencing purposes, because attention is fundamental whether you do training or you do inferencing. So there's multiple versions of this paper, the Splashant 2 and the Splashant 3 as well. And the fundamental idea is primarily the same. It's just the way in which the arithmetic operation or the linear algebra is being applied to make this operation feasible within this context of fused kernel. Okay, and the flash attention, I would just go basic idea here is that this is a picture. If you were to just search for flash attention, this is a picture that comes out. And I did talk to you about tiles. So what tiles is basically, you have this, the query key and value matrix, and this is basically shown as a flat one-dimensional kind of matrix. But essentially, the total size of this matrix is basically number of tokens times the embedding dimensions. And now, so you can break it down into certain X cross X kind of this tiles. And what you're doing primarily, if you just take, so idea is that you have the input is basically this query key and value, and what this block here internally shows is basically the N cross N attention weights that you're going to calculate. So the basic algorithm, the way it works is there's an outer loop that goes over this K and value. So every time you're reading, you're just reading the single tile of key and a value block. You bring it into the SRAM. As I said, the basic idea, this is the block size is probably, the tile size is probably an engineering parameter that you have to consider so that it fits into the SRAM. And then once you have these two values, then you're basically fetching the tiles from the Q kind of from the Q tiles of this Q matrix. And then in one shot, what you do is that, I mean, this algorithm is popular. You can just search and you'll find a good resource on how this algorithm works. In one shot, you can actually do what is called as basically using an online softmax approach. You can calculate this attention weight, and then multiply it with this v vectors tile, and then write it back into the HPM. And all you have to do is to basically keep track of these intermediate values that is written back into the HPM and read in the next cycle and so on. Because when you do something like a softmax, it's not just the tile, it's not independent of each other, but it is basically softmax requires a sum of all the exponents that you calculate in that particular tile. And here, there's other thing that, to stabilize the numerical kind of the computation itself, you kind of also have to have the maximum of this vector that's in this particular row to kind of ensure that, you don't have run into out of, basically you don't run into out of memory or you don't run into outside the numerical precision of what is allowed within the given GPU. Yeah, so I think I covered most of these things. Yeah, using the online softmax. So that's the basic idea of how this algorithm operates in a tiled manner, and basically gives you this one-shot operation to calculate the final kind of this n cross D matrix. Okay, the other idea that is used to kind of optimize your inferencing process is what is called speculative decoding. So this speculative decoding is again addressing the fact that decode itself is a memory bound operation. We talked about it several times. And so idea is that if I simply load in a full large language model and basically generate tokens, one token at a time, as I said, it's not going to be compute efficient. It's not going to kind of be efficient from a GPU utilization perspective. So what else can you do? So what people said is that why not use a smaller model to generate some draft tokens and then use the large language model as a verifier to verify it. So that's the basic idea here. And it seems that this particular technique seems to get you an efficiency throughput of around 2x. So in the sense, like, you could almost double the number of tokens per second that you can generate. So a big jump, I would say, from the inferencing perspective. So I'll explain the idea to you. The basic idea is that, as I said, you have a draft model. You're using a small model here and large language model here. And you can assume that at a given particular time, probably only one of them is loaded into the GPU. So given a given prompt, what you do, you start with the prompt and you use a small model to generate some future tokens. For example, you have a prompt like the orange cat, and basically you basically do the same prefill and the decode operation to the small model, and you basically generate some future tokens. And now what you do is that you give this entire prompt with the future set of tokens, which is again a variable configurable parameter. You would say that, okay, I need say X number of future tokens or K tokens. Give it a large language model, and the large language model now would basically kind of verify it, comparing its own logits or basically its own probability distribution for those tokens. The idea here is that now, so in the sense, if you look at it, because now it depends on, I don't think so. The key idea is that small language models, KV caches and all, cannot be used in large language models. So this is pretty much operating in a prefill kind of operation mode, right? So you're basically calculating it in one shot at a given point of time. Yeah, I mean, at least to begin with. Afterwards, I think large language model can also use its KV caches for that matter. So the big key idea is that the way the large language model acts as a verifier is to compare the logits with the logits of the draft model itself, and then you use a statistical technique like rejection sampling to accept the draft tokens or not. And this particular, it's basically an idea that was proposed in this particular paper, and it's been mathematically shown that if you're using a rejection sampling method, though the distributions of the target and the draft is going to be different for a given set of tokens, by using rejection sampling, you can the probability distribution is going to kind of match up with what the large language model requires. So this is something that comes from sampling theory and so on. I'm not going into the details of how the rejection sampling works, but at a very high level, you can think that if I have, say, I generated 3 tokens, and I suppose I generated some 0.5, 0.1, and say 0.8 for this as logits for this for these new tokens. And if I have something else where I have, like, say, 0.6 and 0.1 and 0.9, so basically I compare my probability kind of distribution, or the logits, or the probability of or prediction probabilities of the large language model with the draft. And when if the large language model is good, then I basically kind of accept is greater than this what is generated with the draft, then I just simply accept it. If it is not, then I kind of accept it with kind of the with the probability of the difference between the large language model and the draft model. And if it is I would say if it is rejected, in the sense that because the probability kind of distribution is significantly high, then then basically you kind of do sampling with some more other tokens, and you kind of accept it or reject it. So this is the basic idea. Is the fundamental idea here is that this is a technique I see. It's a very active area of research. Many variants being proposed in this space. And it seems to be an easy way by which you could kind of push the throughput of the system. So in addition to, as I said, like there are many other techniques that are being proposed in terms of how you select these draft models and so on. So there is there's one technique in VLLM. VLLM supports this other techniques called Ngram, Eagle, and Medusa, and so on. In Ngram, you don't have a draft model itself, but you just take your current you look at your historical set of tokens, like prompt, lookup, max tokens, and for those set of tokens, and for max tokens, and then you basically look for these set of max tokens. Are there similar kind of a similar set of tokens that were generated earlier? And then you basically look at the future tokens and then suggest it as your draft tokens, and then you do the same kind of, you can run the same rejection sampling techniques to accept it or not. Then there is another variation where you have some proposal like Eagle. The idea is that I told you one aspect of this draft model is that you can't choose any draft model. You want to use a draft model that is giving you the logits that produces that generates tokens whose probability distribution matches that of the large language model. Okay, so this is next slide. I probably talk about how what are the different considerations of how you choose these models itself, but that's the main thing. But if you have any random model and who's going to generate anything that doesn't match, then you're pretty much kind of doubling the amount of work. You're not making any progress itself in terms of the token throughput. So there is this Eagle that basically works on the same large language model. It keeps the embeddings. The large language model head is the same, but replaces the transformer stack with large lightweight MLP. So you have much leaner model, but representative of the large language model and so on. And then there's another technique called Medusa, where Medusa is based on the fact that you take the large language model, and normally all the large language model has a single head, right? So basically, if I have n tokens, you have an head for say each one of those tokens, and then you're generating the basically a probability distribution for over the vocabulary set for every token asset. So in this particular case, you just don't predict for the next token. So if you have k tokens, I don't just predict for k+1. I predict for the nx tokens. So I basically call it next k tokens here. So it has multiple heads in that sense. And then I use that as my I propose, and I take those and basically use it through my large language model to kind of validate whether those tokens are acceptable or not. So how multiple draft even running CPU can increase. So recent approaches also show how multiple draft models even running on CPU can increase throughput. So in the sense, like here we are talking about everything running in a GPU, but then as I said, this is an active area of research where people have been looking at, hey, can I run the small model on the CPU and propose tokens and use a GPU for the more kind of large language model compute and memory intensive tasks. And as I said, how do you choose a draft model? Generally, it has to be a function of the large language model itself. So, for example, if you have the Llama family, you have 70 billion parameter model, you choose the one that is probably the smaller one. More because generally, they have been trained on similar data sets and so on. You can use the same tokenizers, correlated prediction, but still requires two models. Distilled model, train smaller student to mimic larger teacher, higher alignment, fewer mismatches. Or you can take a model and do the quantization of it, an int8 or int4 version as a draft model, and which is going to be faster with similar prediction. So there are different ways in which you can choose this draft model. Okay, so the other aspect, I would say another use case that these large language models have to consider is about constraint decoding. So the constraint decoding is basically, I would say, very an use case that would come particularly with software systems interacting with these models itself, where you want the output in certain structured format. Okay, so general format for kind of that is easy to parse is basically the JSON mechanism, JSON based on JSON data structures. JSON schema. So idea is that when you give a prompt, you basically tell the model that, hey, I want it in this JSON schema. And so what happens is that earlier approaches would take this JSON schema, you convert it into certain regular expressions, and then some finite state machine. And then this finite state machine works in lock-in step with the kind of decoding process to say that what set of tokens is accepted or not, so that, because you want the kind of the outputs to kind of map to the actual expected the structured output that's required by this finite state machine. So SGLang combined the logic of decoding with SSM, with the FSM required in the output. So earlier, for example, this is basically showing a comparison of the optimization that was done with SGLang versus some of the other earlier techniques here. So if you take an earlier technique here, the basic idea is that you are basically giving this you're giving this prompt where it says, please fill in the following information of Harry Potter, and basically you're giving this key value. You're basically giving this input in terms of name, age, and house. So that the model itself is expected to generate Harry 15 and Gryffindor. So Gryffindor. I'm sorry, this is the house name, whatever it is. So idea is that this should be the output to the end user, right? So the key thing is that you said, okay, this is a structure and this is a finite state machine, which is converted into some kind of finite state machine internally by the inferencing system. And you are taking this output, you are kind of appending it to this structured input that was given to you before you generate the final output. So this is, if you were to do the implementation before SGLang had this the decoder kind of generate every every character in this particular sequence that is desired. And when you generate, you also are basically doing things like you're masking and so on to basically ensure that if it is giving some other generated token, then you basically would have to kind of go back and correct it and regenerate and so on. But somehow with the things with SGLang did is to basically to avoid this kind of complexity of about the decoder to generate every character as required by this JSON schema. Rather, they had a mechanism by which they combined the decoding and the FSM in a more intelligent manner, so that you could the decoder is only being called now where it's actually required to generate output. So you have this particular prompt, you basically inject this in this particular kind of a key that you want, and then you generate the tokens and so on. So I would say this is again going into this whole idea of how FSMs have to be managed, how regular how regex is basically processed within the tokens itself. It's a complex problem, and what I'm just giving you is a very kind of a hand wavy kind of an idea of how things operate here. But this is a very kind of and a very intense area of research as to how do you basically get structured outputs, and that's required. And as I said, this is more important for machine-based interactions rather than human-based interaction, because as when we interact with chatbots, we don't request it in a particular format. Though sometimes you might say that, if you're generating latex and things like that, you might say, okay, I need certain outputs in certain latex format. But to do this efficiently is what this entire space is looking at, to ensure that, because you don't want to kind of you want to kind of maximize your token throughput, in spite of the fact that you have to work within this constrained regime of operation. That's a basic problem here. Okay, next is, okay, the next idea of optimization is what is called as the prefill and decode disaggregation. So the basic idea here is that so we talked about this two aspects of what is prefill and decode, and the one of them being compute and memory bound. If you were to do a very kind of a naive based of scheduling of, we also talked about this head of line blocking issues. So this is where the scheduler is not making a differentiation between the prefill and the decode kind of operations that is being processed. You might see that a prefill is actually taking inordinate amount of time, and basically in some sense basically blocking the generation of tokens for something that's already in the decode phase. So the main idea here is, and the main use case for this comes from the fact that there is this entire area of test time compute that is becoming more and more important, because if you look at even ChatGPT, they have something like a thinking mode and so on. So you are basically giving a prompt and you're allowing the reasoning, you're allowing the model to kind of reason, generate tokens, and before it gives you a kind of more intelligent kind of an answer. So this test time compute is one of the driving factors for why inferencing is being kind of looked at, is basically being proposed, or a new structure is being proposed to kind of disaggregate the prefill and the decode phase. So idea is to physically decouple the prefill computation from the decode. The idea is that, so you have in this particular picture, you see that you have a set of machines or set of devices dedicated for the prefill, and set of devices dedicated for the decode. Idea is that now the thing is that the decode is not getting would not be interjected or would not be preempted by anything that's coming from the prefill, right? So you can generate, so all the requests comes in, it could be RAG requests, or it could be simple user prompts or whatnot. You can generate the first token, you generate the prefill, generates the KV cache, and then you use some kind of a messaging protocol here to transfer the KV cache. Or you could even do things like RDMA kind of operations. There's things like Nixel and so on that's being proposed between the two clusters to directly write the KV caches between the device memories and things like that. So you can do this kind of operation of directly taking the KV cache and writing at a very high speed. If you have very high network bandwidth here, that's a fundamental assumption, is that these operations are very fast. So by the time the request is kind of comes to the decode phase, then you have the KV cache to start generating the tokens. So here it shows that, okay, first token is generated with prefill, and the remaining tokens are being generated by this decode cluster. Again, this idea may not be suitable to all the inferencing service provider. It all depends upon the distribution of the input and output sequence lengths. So this is a good diagram that shows that, okay, with how, for example, there is, if your input sequence lengths are much smaller, then that means that your prefill phases are not going to be that compute intensive. Then you can go with an aggregated kind of an approach. An aggregated approach, again, could also mean that you have multiple GPUs at your disposal, But fundamentally, you don't distinguish that you have not clustered those GPUs dedicated for prefill or decode itself. So it's still an aggregated. It can any GPU can be used for either prefill or decode as such. So disaggregated would mean that you have created this partition of resources, and there is other with much higher sequence length. You can also think about disaggregated context parallel kind of thing. So again, context parallel would fundamentally say that your prefill phase itself or your decode itself, the context it can be within a given request, the generative task itself can be broken down into multiple contexts, which is processed on multiple GPUs and so on. Yeah, we talked about this, that you need a new communication infrastructure there. For example, Nixel and the multi-layer storage can be used for KV cache. So now you can think about if you're talking about different tasks, a task that requires immediate response versus a task that where the service layer objectives can be higher. So you can use much slower caches to store those KV caches. And from where, and when the decode request comes in, then you pull out from that slower memory to kind of do your KV caches. So this gives you a complete decoupling and the flexibility of what kind of storage mechanisms can be used for this KV caches as well. And this one was actually first proposed in this paper, from folks in UCSG, and basically they saw that okay, there was immediate gain by doing this kind of approach. So this is coming back to that Pareto regime that I had introduced earlier. And if this is again a paper that was a presentation on Dynamo from NVIDIA that shows that if you were to use this kind of disaggregated mechanism, and you could actually bump up your throughput of the system for a given tokens per second per user, you could bump up the total throughput of the system by 2x. And so this, which is quite desirable. Here you can think about that they have, and this was again tested for different variations of ISL with cached, uncached, and with different lengths of the OSL kind of distributions itself. So yeah, so basically there is some experimentation to validate that, okay, this seems to work in certain scenarios. And another extension for this is basically introducing another network function called as KV cache router. So what you do with KV cache router, now you basically introduce this kind of set of new kind of clusters of specialized GPUs dedicated for prefill and decode. You could have another kind of function here that is a KV cache router now do things like policy-based scheduling. So if I have a KV cache router, it's basically trying to take in this request and deciding, hey, where could I actually send this request towards, right? And this policy-based scheduling can be based on the fact that I have a state of the KV caches on this prefill nodes or in this decode nodes, and I could send it to the node that has the maximum matching for a given for the given KV cache and so on. So ideally, one easy way to do it is that okay, you have a state for all the prefill nodes here, and because if you're doing prefill, then you just send it to the particular prefill cluster and basically have it done. The other approach is that it need not you can use multiple. I would say there are multiple ways you can handle this problem. So the other approach is that it always need not take this prefill and decode route. But if it's a very small request, then you don't need to kind of send it to the specialized cluster. You could just send it to a decode cluster. It's just that you don't have the KV cache. It'll just do the generation like normal generation and send the result back to the entire user. Yeah, so I did talk about this. The KV cache router is basically it tracks the KV state in each worker node, and the statistics. You need telemetry information that comes from these nodes to take this kind of decisions. So it also shown with some experimentation that KV aware routing can be 2x faster and so on. So yeah, so this is again, as I said, people are going into a more distributed approach of doing inferencing at scale, and I wouldn't be surprised. Probably these are also used in production as such with the kind of volumes of requests that people have to deal with. This is NVIDIA's Dynamo that has a kind of an open source project as well, and that has a full-fledged implementation of this internal communication layer. So they have functions like the smart router. They have disaggregated servicing is more the idea that I just discussed. So they have the prefill workers, decode workers, distributed KV cache, and they have this Nixel library that interconnects the transfer of KV caches from the prefill to the decode and so on. And they have mechanisms by which these this telemetry information from these workers can go to the smart router so that it can do this kind of can do this policy-based decisions. And I think they have something like a planner as well, uh, basically where you are keeping track of the demand that is that these prefill workers are basically having to kind of absorb at a given point of time and plan to kind of scale these nodes. So I think they have mechanism by which you can also do runtime scaling, horizontal scaling of these clusters, add more prefill worker nodes if required to kind of handle these kind of scenarios. And we talked about this KV cache offloading can be object and host memory and so on. But again, all this fundamentally depends on the specific use case you're dealing with and the SLOs that you have to cater to the end user. All this idea that I spoke about here is also being considered from a Kubernetes perspective. So Kubernetes has these functions like Envoy and so on, which is a very popular load balancer and open source load balancer that's used in systems today. And these are being kind of extended for handling functionalities very similar to the KV cache router functionalities. And this is, I think, a fairly new project that has started off and are basically kind of are focused on handling inferencing at scale. So basically, you could have under the Kubernetes cluster, you could have a cluster of nodes. Here we show that all these nodes are basically being served by the VLLM implementation. And they have this bus that is basically being used from NVIDIA's implementation, the Nixel. And then you have some other KV cache mechanism by which you can, KV cache is being shared using these projects like LM Cache or Dynamo, KVBM, host memory, and so on. So all these mechanisms that I just spoke about under the Kubernetes hood, people who are aware, it's a very it's a very common way to kind of deliver container as a service. It may just makes it easier. Everything is declarative and so on. So you could easily extend. It's natural to understand that Kubernetes can be extended to handle this kind of scenario, this particular use case as well. Okay, and now coming to, I would say probably this is one of the last topics I have. Is basically on the parallelism itself. So how the other dimension which you could kind of increase the inferencing performance is by going through this parallelism route. If you know, parallelism is a basic idea where you are so the whole notion of parallelism, I think, was, I mean, it was primarily used a lot in the training world. So where you had to train these huge models with large data corpus, and the way the parallelism applied in the training world was that, okay, you used because the models could not fit in a single GPU, you kind of sharded it across multiple GPUs, and you use things like tensor parallelism or pipeline parallelism in that context. So if you had a cluster of say 1,000 GPUs, you inside the server you basically used tensor parallelism from the fact that because you had things like your NV switch and NV link that gives you a very high bandwidth, and then within servers between servers you would use things like pipeline parallelism, and then so the cluster of nodes basically implemented one instance of the model itself, and then you have clusters of this kind of replicated doing data parallelism with different batches of data and so on. So that was a basic idea that was used in the training world. Similar things you can also, but from inferencing perspective, I think you have to see it from a different perspective, in the sense that for inferencing, the basic idea is that you want to maximize throughput and you want to reduce latency itself, right? So idea is that you could easily double the throughput of the system if your system can be kind of can be fit into a single GPU, right? I could just simply take a single server and have 8 GPUs and have the if I could directly increase the total number of the total throughput by 8x. But just if I'm running with something like something like a SLMs or a large language model that fits within the request of within the resources of a single GPU. But even then, I would say that because you are running different batches across the GPUs, it fits into this thing about coming to this parallelism being called as a data parallelism approach. The other thing is that what happens if your model doesn't fit in a single GPU, then you basically have to you have to shard it across multiple GPUs. Then you need to think about whether you're using tensor parallelism or expert parallelism. So tensor parallelism is primarily about just kind of sharding the matrix multiplication across GPU, and then you do an all gather or an all reduce to basically kind of recreate the whole the original kind of, you can say, the tensor vectors for each token, and then go to the next layer of processing and so on. So again, I did mention about that why tensor parallelism could be used. Tensor parallelism is generally used within a server because of the high bandwidth interconnect. But there is a trade-off when bigger batches are applied to the TP alone. So there is there are some engineering considerations of what parallelism could fit for a given model under considerations. So by default, it's not good to just, if I have like say 64 GPUs, it is not good to just say that, okay, I take this entire GPU cluster and just do a TP on top of it, which is not probably the right approach. So you have to think about, would it be better to kind of break it into groups where I apply data parallelism. Under the data parallelism, I used tensor parallelism to kind of maximize the throughput. So what I'm trying to get at is that your end objective has to be clear in terms of how we use the GPU resources to kind of meet the objective that you want from a system perspective. So again, the other consideration when you do parallelism is the communication overhead. So whenever you do, because you have now spread out the model across multiple GPUs. So you, at the end of the day, your final kind of a decode token is coming out at the end of that. The entire chain of GPUs have kind of acted upon it. So there is a certain communication cost that goes into kind of transferring the data, doing all reduce and reduce gather and so on. So this is a big consideration when you actually apply parallelism for the inferencing as well. And so, yeah, this basically picture just shows that, okay, you don't apply any parallelism versus you do some kind of parallelism, you can increase your tokens per second. So, yeah, so this is a basic idea I'm just giving is about how parallelism is used. Another point I would also like to mention is in terms of this KV cache, the other important thing when you're going from training to inferencing itself, the other indeterminate factor is about, or undeterministic factor is about the KV caches itself. So when you plan for this GPU, you can't just talk about the amount of memory required for the weights itself, but you have to also think about the amount of amount of data memory that would be consumed by the KV caches itself. So when you do a capacity planning of the system itself, you have to, sometimes if it's a 500 billion, suppose it's a, say you can say 500 billion parameter model, you say, okay, I need 500 GB. If I to just say that, okay, I have 2 GPUs that has 200 GB each, and you say I need 3 GPUs, but that would not do the thing. You probably, because you have not considered for the KV caches itself. So you have to consider like probably 6 GPUs or 50% of the GPU memory is at least there for the KV caches and so on. So this is another consideration when you do kind of think about parallelism in the context of inferencing. So I just wanted to bring out one. I think this is one of the latest work that has come out of things like the large scale expert parallelism implementation of the DeepSeek V3 model within the in the context, basically using SGLang. And DeepSeek V3 itself uses these two basic constructs of mixture of experts and multi-latent multi-head latent attention mechanism. So if you have an idea of what a mixture of expert model is, so we talked about the transformer layer itself, the transformer layer having the attention and the feed forward neural network. So in mixture of experts, what happens is that you don't use this bulky FFN layer, but you have multiple of these FFN layers, smaller FFN layers. And so if I have, and if a normal dense, they basically talk about dense FFN and a sparse FFN to distinguish these two scenarios. If I take a dense FFN, if I have like say 10,000 parameters, my MOE could be implemented as basically say 10 mixture of experts, each having something like say 100 parameters, or sometimes the parameters could also be more than the actual parameters of a full dense FFN. But the key advantage of doing this kind of this breaking down or splitting down is that they use some kind of a routing and a gating function that allows you to only activate the set of experts that you require for at a given point of time. So you can save on the total kind of, you can say, the resources, memory resources, and the compute resources. While in a normal dense FFN, you have to kind of to go through the entire FFN process, but in MOE you can selectively. It's selective in terms of what kind of experts gets activated at a given point of time. So this particular implementation that they did enables a hybrid of a data parallelism techniques and TP parallelism to basically consider the fact that this is again coming to the point I made earlier, that how these different inferencing systems are catering to specific implementations. So in DeepSeek V3, we have called it the multi-head latent attention. So it is simply a single KV head that is used for all your basically during the entire kind of the attention mechanism. And the basic consideration was that if I were to use simple kind of tensor parallelism, then these KV heads get replicated across all the GPUs. So the way they avoid this replication is basically using technique of data parallelism. So you have a batch one, you basically use data parallelism across multiple GPUs, but operate on different batches of data. Then you do an all gather, and then you do tensor parallelism here. So in the sense that they've used different parallelization techniques in different layers of the model itself. And they use different techniques for dense FFN and sparse FFN. You can see that the sparse FFN, they have an implementation called as DPEP dispatch. So you can say that FFN itself is more or less a very stateless kind of an approach, in the sense that I would say stateless in the sense that you're not carrying it doesn't require the historical KV cache and so on. So given a given token, you just apply your routing or a gating function to decide which FFN it has to go through. For that, they have some kind of can say a distribution function implemented here that allows you to do a dispatch here and send it through any of these expert kind of implementations, expert parallel EP blocks here, and then do a DP-EP combine and recreate this batch for the next cycle. So as I said, this basically goes to the fact that there are certain functions being implemented for a specific kind of transformer kind of variations that are being proposed. And the whole idea of this, particularly from inferencing perspective, is to kind of, as I said, to use your GPU resources as efficiently as possible to maximize your token throughputs and so on. And I just wanted to show some, I think probably this is, you can say, some state of the art, at least in the public domain. Probably these are some things that are also getting, these are benchmarks probably, or probably better benchmarks that probably even implementations like OpenAI's or the other production systems might be seeing. So they try to kind of recreate or achieve what DeepSeek has been kind of achieving at their end. So they have certain profile, and I think they have been able to kind of implement a similar kind of, I would say, a system where you have where you are using this PD disaggregation approach. You have a prefill worker nodes, and you have a decode set of worker nodes. You have a KV cache implemented, and this system was implemented using 12 servers, so 12 servers, so 96 GPUs, 24 GPUs used for prefill, 72 for decode. And the result is that you could have prefill input throughput of being processed of around 55,000 tokens per second per node, and an output of around 22,000 tokens per second per node. Again, this is, I would say, when they say this per node, it's basically saying is you are getting certain throughput. You're getting certain token throughput, and you basically divide it for, I think you basically take the fact that you're doing it over, say, in this case, 72 GPUs, and that's what the per node kind of metric here signifies. So just to basically show, normally if you look at a lot of research papers, you would normally see like 100 or 200 tokens per second. These are like the higher ends, but then as I said, parallelism gives you that kind of entire boost. You are working with multiple workers. You are applying the best of the kind of the state of art kind of implementations, PD. Here you have this, you're using expert groups and using this DP kind of EP kind of libraries to kind of distribute the FFN operations and so on among the expert groups. So I would say this is kind of, I would say cutting edge right now in terms of what the inferencing systems are achieving as of today. So yeah, I'll just close off with just going through some of the basic. I talked about VLM and SGLang. So what does the systems look under the hood? So if you take a single basically a basic implementation of a VLM system, generally you bootstrap the system with some VLM config. So you basically tell exactly how, say, probably what kind of parallelism you want to operate it on, or certain other parameters, like, okay, of course you have to identify the specific model that you have to load and so on. So that's something that you give as input to the system. But internally within the system itself, you have things like the model executor and the scheduler and so on. There's a request that is coming in. There's an input processor, there's an output processor. The data is basically, the requests are coming and sitting in a waiting queue. The scheduler decides which of these requests gets scheduled in a given iteration. There is something like the KV cache manager we talked about in terms when we looked at the page attention, where all this paging, the paging data structures are managed. And then once the request, the generated task is completed, then you send it to the output back to the end user. Again, going into the KV cache manager itself, this is basically keeping track. This is the actual physical logical layout of the GPU memory itself, the KV cache memory, and so then you have a representation of it in the CPU space with this block IDs mapping to saying that, okay, these blocks are kind of are available and free to use. So when request comes in, you're basically taking from this free pool and basically saying that, okay, once you have a prefill, you have a KV cache generated, then you can write those KV caches back into these blocks that have been assigned by the scheduler and so on. So this is the basic architecture of the system, and then you have all these functions that's currently supported with VLLM. We talked about the page attention, chunk prefill, prefix caching. Guided decoding is like the kind of the constraint decoding we spoke about. We have speculative decoding. So this mechanism, gives you ability to kind of load in multiple models and do speculative decoding. It supports the segregated PD, prefill and decode kind of inferencing as well, quantization and so on. So everything that we discussed is basically discussed today, and these are all active area of research. There's also, I think, there's a router SIG within this group that's implementing the smart router equivalent functionalities as well. Similarly, with SGLang is, I think, a little bit more, I would say, offers you more features in terms of they have a domain-specific language here that can be used to programmability express what kind of decoding functions processing or say prompt processing function that you want. So in this particular case, you are basically giving an image and you're basically saying that I want to evaluate this image and generate 3 responses and 3 different dimensions of clarity, originality, evidence. So this all can be expressed using their DSL, and you give it to the system, and the system would analyze this and basically allow you to generate responses based on what based on your kind of your declarative requirements that you've expressed here. So in a sense that um, you have again all this being the reason why this is also helpful is because of the radix tree and all that they maintain internally to kind of process and page the KV caches and so on. And it has very similar at the high level. You have the client, you have the structured language front end, which is what this is. And then you have the API server tokenizer. Everything has to be tokenized before you process it, put it through the GPU. And then you have a scheduler similar to what the VLLM. And if I were to understand, I think some of this code that is also based on the VLM code because it's primarily come from same lab. And we talked about all these functions that we have. And radix attention, continuous batching, multimodal support, both are active projects and they're pretty much kind of, I would say, trying to match up with what each other offers at a given, basically considering to kind of minimize the gaps between the feature sets that both of these offer currently. So this is a very high level of HGLang. Yeah, and this is what I hope, this presentation was useful. As I said, this is I would say a very an early days from an inferencing perspective, from the fact that you are more or less catering to a single kind of user requirement is primarily from, I would say, chatbot perspective and so on. But once you go into things where Transformers itself is doing generative responses for more real-time applications, those inferencing engines are expected to be more complex, and the scheduling and all is supposed to be more kind of has to be more intelligent. As I said, this is an active area of research with inference system required to serve multimodal agentic capabilities and so on. So I hope this was useful to you all, and I can take a few questions that you may have. Thank you.
Excellent presentation, and of course it was a little longer than expected, but I think people stayed here to understand. And anyone wanting to ask question, please raise your
I think Daniel had some question, I guess. So.
Unmute yourself. Yeah, go ahead. Daniel, go ahead.
Am I audible?
Yeah, Daniel.
Yeah, you are.
Excellent. I have a question on that concerns me with regards to the optimization. There are charts, and I see them often, about tokens per second, but there's no measurement of accuracy, and that's critical in many applications. You know, banking, loans, automobiles on the road. And I understand that accuracy is very difficult to measure. I imagine it similar to being grading essay questions on the final exam. So
As I said, like this is something that I added from my end. That's why I put an asterisk there. Accuracy is not something that they measure from an inferencing system perspective, because this is a model characteristic. Okay, so generally when you talk about inference system, for them it's like, how do I take a model and start giving you the best performance for the resources that I have at my disposal. That is a basic idea here, but accuracy is more a measure of a measure that comes when you actually train models itself. For example, totally get your point. This is a very important thing, because a lot of the accuracy metrics are based on standard benchmarks like MMLU or some of the things like, whether you're good in measures that map to kind of summarizing texts or solving problems and so on. Not for specific verticals that you just mentioned. And I think this is where I think there is also a gap if you look at mostly from a model development perspective, and how you would take pre-trained models and kind of make it more kind of purposeful for a given domain and so on. But here I was saying that, okay, this could be, this is not something, as I said, this is my addition to this whole metric thing. I was saying that, okay, this could be one of the differentiators how inferencing platforms could be more intelligent in terms of taking a given user response. And if I have a user request and if I have 10 models to choose from, then I would probably choose a model that would be more appropriate to answer that particular prompt than some other model. So this was
very, yes, that's very clear. I guess my last question, there was a slide where you showed the performance with DP, and then it showed the quantized models having lower performance in tokens per second than non-quantized, and I found that puzzling. It's toward the end. It's like 5 slides in from the end.
Oh, okay. This one probably. Okay. Is it this one?
No, what? Yes, right here on the bottom right-hand corner. I don't understand why the quantized is so slow.
Okay, so we have the prefill, and so this shows the different models of. Okay, is this it just where I don't know. I'm saying, do you have any quantization mentioned here?
TP16, I believe, is a marker.
Oh, okay, yeah. Oh, no. Okay, so this is okay. This is not to do with quantization itself. It's to do with the parallelism itself. Okay, sorry about that.
Okay,
So,
well, that makes sense. Yes.
So this is basically saying that you're applying a tensor parallel over 16 kind of nodes,
gotcha.
or an EP,
Perfect.
or you're distributing the MOE over 72 devices and so on. Yeah,
that clears everything. Thank you very much.
Yeah, thanks, Daniel. Yeah, thanks for your questions.
Anything? Sujay? Marani?
Fantastic talk covering lots and lots of material. Thank you so much.
Yeah, as I said, each one of this topic that I mentioned here is itself an area of research. So, I mean, my idea was to just give you a kind of a flavor of what the basic problem is, and say the most popular solution that has addressed that most effectively, in some sense. But if you were to take each one of them, you could actually find some other solutions as well. Yeah, I know it is a little bit a lot to digest here, but I hope at least, I'm assuming the slides will be available, so you could always just use it as a reference for your future kind of investigation and so on.
Thank you, and thank you for the slides that are coming.
Yeah, thanks, man. Yeah.
So, any question? Last call. 1, 2, and 3. So before I stop recording, I just want to thank Ravishankar Ravindran, a great colleague of mine, I would put it. I have worked with him for several years now. And like my go-to person, if I even want to do a matrix multiplication on semiconductor, I'm trying to find a solution for that. So whether it's semiconductor, whether it is quantum, whether it's high performance computing, communication, networking. So I've run through him for many things, and very happy to see him present a very open presentation, and we'd like to definitely share with you everything that is available, and slides will be available. Once recording will be available probably in a day, and I may need some cleanup because in between there are some talk coming in. Hopefully we'll clear that out, and with that I'll stop recording and you can ask anything offline.
Thank you. Bye-bye.
Yeah, thanks a lot.